Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 38, Organic Chemistry 1. Today we'll start on chapter 9, Chemistry of Alkynes. We will talk about nomenclature, acidity of terminal alkynes, preparation of alkynes, reactions of alkynes, dehydrohalogenation reaction, halogenation reaction, hydration reactions, ozonolysis of alkynes. And later on we'll talk about synthetic strategies. Let us start with nomenclature. First step, find the longest continuous chain of carbon atom that includes the triple bond and change the ANE with YNE. The ANE of the alkane, you take it out, and instead of it, you write YNE. Second step, number the chain from the end closest to the triple bond, and the position of the triple bond is designated by its lower number carbon atom. Third, give the substituent their numbers to indicate their locations. You have to take care of this one. When additional functional groups are present, the suffix are combined to produce the compound name. For example, if you have double bond, a triple bond, the suffix will be alkene yen. You write the en and write the location, and yne and write the location before it. A double bond and a triple bond, if you have triple bond and alcohol, then you write yn and then all. Yn for the triple bond and ol for alcohol, and so on. You have to know the priorities. If you have acid, then the compound will name by the acid functionality, the highest priority. Then comes ester, aldehyde, ketones, alcohols, amines. Alkene and alkynes have the same priorities, and we will come to it later on. Alkanes, ethers, alkyl halide is the lowest one. Yes, we have the IUPAC name, but some of the compounds have common name. Here, ethene, ethine, has a common name acetylene. Here is 1, 2, 3 carbon. Propine, common name methyl acetylene. Butanene is ethyl acetylene. Ethyl acetylene. What about butene? It's dimethyl acetylene. Dimethyl acetylene as a common name. When it's getting complicated, there is no common name, all right? Let's see here the IUPAC for this one. The longest chain will be the one containing 12 carbon, so it will be duodec. We number the chain to the shortest, by the shortest way to the triple bond. So it will be 1 from here, 1, 2, 3. So it will be duodic 3N. By numbering 1, 2, 3, 4, 5, the chlor will be on carbon 6, methyl, 2-methyl will be on carbon 7, and 1 on carbon 10. So it will be according to alphabet. Okay, here is C and here is M. So it will be 6 chloro, 7, 7, 10 trimethyl duodic 3N. Here, the longest chain contains 8 carbon, so will be oct. Okay, we have here 2 triple bonds, so it will be di-N. On carbon number 1 and carbon number 5. And we will have methyl on carbon 4. So it's 4-methyl octa 1,5-di-N. For this compound, the long chain containing 9 carbons, so it's none. It contains triple bond and double bond. Triple bond, if we name it from this side, will be number 1. And the carbon will be number 4. And that's the shortest. They are in different positions, right? And we have methyl on carbon 3. We have ethyl on carbon 6. We put them alphabet. So it will be 6-ethyl, 3-methyl, non, 4-ene, 1-ene. And the geometry configuration around carbon 4,5 double bond is E. So it is E, 6-ethyl, 3-methyl, non, 4-ene, 1-ene. If it happened that you have the double bond and the triple bond are terminal or in the same position, if we number from the right or the left, then you select the shortest to the ene, to the double bond. So we start here number 1. So it will be 6 carbon. We have double bond and triple bond. The hex 1-ene, 5-ene. So if we have the same compound, but here we have substituent on carbon 4, then it will be 4-methyl hex 1-ene, 5-ene. Okay, if we have it here 1, 2, 3, or we number here 1, 2, 3. They are on here number 2, and here is number 2 for the ene, right? If they are on the same position, then we select the shortest to the ene. So the name will be 2-ene, 6-ene. And double bond, once again, E configuration. So it is E oct 2-ene, 6-ene. For this compound, we have 2 functionality, alcohol, which is more senior than the triple bond. We have both of them. Select the chain contains both functionality, and then number the system to the shortest to the OH, the senior group. So OH will be on carbon 3 and the triple bond will be on carbon 7. So it will be dec 7N 3 ol. If we have compound triple bond CH like but 1N, we call this terminal alkyne. If you have compound where here is R group and here is R group or R prime group like hex 2N, we call this internal alkyne. We call it internal alkyne. Terminal alkyne means that it ends with CH, right? Draw out compound 5,5 dimethyl non 3N. So what you will do, write the chain contains 9 carbon and from any side write 3N. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we number it from this side, fine. And on carbon 3 we write the triple bond. And then we insert on carbon 5 dimethyl 1, 2. So here we are. That's the structure. We just fill in the hydrogens. That will be the compound 5,5 dimethyl non 3N. Provide a systematic name for the following. Provide the systematic name. When you read systematic name, means a IUPAC name. Okay? So this is a compound. Select the longest chain. So containing the triple bond. And then number the shortest way to the triple bond. So this will be number 1, 2, 3, 4, 5, 6, 7. We have substituent on carbon 3, 4, and 5. If we select the 7 from this side, 1, 2, 3, 4, 5, 6, 7, it's 7 carbon. But here you have only one substituent. And you recall from the nomenclature, we said the more substituted, the correct structure. So this one will be the correct selection of the longest chain. We have on carbon 3 butyl group. We have on carbon 4 we have ethyl group. On carbon 5 we have methyl group. And then we have the triple bond on carbon 1. So you say hept 1N, or the old way is 1 hept N, or 1 heptine. Okay? All right. Physical properties. Alkynes are nonpolar, unsaturated hydrocarbons with physical properties similar to alkanes and alkenes of equal molecular weights. Of course, the difference will be 4 and 2 mass unit. Alkynes are quite soluble in most organic solvent, including acetone, ethers, methylene chloride, chloroform, and alcohols. Alkynes are insoluble in water. Compared to alkanes and alkenes, alkynes have slightly higher boiling point. Acidity of acetylene and terminal alkynes. We have covered these topics in acids and bases chapter. We will go just very fast over it to remind you. With the bases, reacting acetylene of pKa 25 with very strong base sodium amide to give sodium acetylide and ammonia of pKa 38. Recall, as pKa value smaller as the acidity increases. Well, pKa here is 25 and for ammonia is 38. Which one is a stronger acid? Of course, acetylene will be the strongest acid since it has smaller value of pKa. Recall that the equilibrium of acid and base reaction will always favor the formation of weaker acid and weaker base. Here we have weaker acid and base in the right hand side, so the equilibrium will go shift this way with the formation of sodium acetylide. If we react acetylene with sodium hydroxide to give the acetylide and water in this case will be the strongest acid, pKa 15.7, acetylene here is 25, so the equilibrium will go shift this way and the formation of sodium acetylide will not be achieved. Using the information of pKa value, predict the position of the equilibrium of the following reaction. This one. The first step is to compare pKa value of the two acids to determine which one is weaker acid. This one will be close of pKa of acetylene, and this will be for the carboxylic acid, acetic acid. Recall that higher pKa indicate weaker acid. So alkyne is a weaker acid. The equilibrium will favor the formation of weaker acid and weaker base. As a result, the base in this case, acetate, is not sufficiently strong to deprotonate the terminal alkyne. Here a pKa 25, here is a pKa 4.75, so this will be the strongest acid and this will be the strongest base, and the equilibrium will shift to left. Okay? Preparation of alkynes. Alkylation of acetylide ion, so having the terminal alkyne with a strong base like sodium amide, we said that we were going to form the acetylide ion that is a very powerful nucleophile. So in this case will act as a nucleophile, and if we have primary alkyl halide, we'll go SN2 reaction with ejection of X minus to form R triple bond R prime. So having put 1N with sodium amide will form put 1N1-ide, SN2 reaction to form hex 3N. If the backside approach is hindered, the acetylide, instead of acting as a nucleophile, it will act as a base, and elimination reaction will take place. So put 1N1-ide or ethyl acetylide reacting with a secondary alkyl halide will undergo E2 reaction, and the acetylide will act as a base, abstracting the hydrogen, forming double bond, ejecting Br minus to form but1N and prop1ene. Show how you might synthesize the following compounds using acetylene and any suitable alkyl halide as your starting materials. Number 1, bent1N. Bent1N, this is the structure. We add here 1, 2, 3 carbon. So we start with acetylide and alkyl halide contains 3 carbon, that will be propyl bromide, for example. So having the acetylide reacting with one equivalent sodium amide to form acetylide, acetylide with primary alkyl halide propyl bromide will form the desired or target compound, bent1ene. If you have to synthesize bent2N, this is a structure. So we have to add methyl group on one side and ethyl group in the other side. Start with acetylene, one equivalent of sodium amide to form acetylide, reacting with ethyl bromide to give but1N. Then react this compound again with one equivalent sodium amide to form the acetylide, reacted this time with methyl bromide to form the desired molecule. We can start by reacting with methyl bromide, then the second step ethyl bromide, or as it showed here, start with ethyl bromide, then methyl bromide. Same tactic. To synthesize cyclododecene from acetylene, if we cut in here, this will be negative and this will be positive. So alkyl halide make this partially positive. And we can get the acetylide from the acetylene. Cutting in here, once again, this will be negative and this will be positive. Okay, so starting with acetylene, one equivalent sodium amide to form the acetylide. React the acetylide with 1,8-dibromo-octane SN2 reaction to form this species, which upon reaction with sodium amide again form the acetylide in here. Internal SN2 reaction will lead to the formation of the target molecule. In the intramolecular cyclization, it must be carried out in dilute solution. So SN2 will be intramolecular reaction instead of intermolecular reaction between different molecules. It will be within the molecule if we started with dilute solution. Okay? Double dehydrohalogenation of alkyl halides led to the formation of alkynes, starting with vicinal dihalide, where the two halogens attached to two adjacent carbon within the molecule, or geminal dihalide, where the two halogens attached to the same carbon atom. If we treat these compounds with excess sodium amide, alkynes are the product via E2 mechanism. So the first molecule of amide acts as a base, abstract hydrogen, forming double bond, ejecting halide ion. Second amide again act as a base, abstracting proton, forming triple bond, ejecting halide. In case of terminal alkyne, a third molecule of the amide will abstract the acetylenic hydrogen, forming acetylide, which then can protonated with just water. Sodium amide can be prepared by the reaction of sodium with ammonia gas, but it is usually prepared by the reaction in liquid ammonia using iron 3 nitrate as a catalyst. In ammonia, sodium amide forms conductive solution consistent with the presence of NaNH3,6 cation and NH2 anion. Here are similar reaction conditions for the transformation of the dihalide, dibromo compound in this case, to alkynes. Starting with the vicinal dibromide, using base and solvent, we get vinyl bromide, and depending on the structure of the substituent, R and R prime group, different reaction conditions could be applied. So if we have R aryl or alkyl and R prime H or aryl, we can use sodium amide in ethanol and ether. If we have R aryl or alkyl and R prime hydrogen, we can use potassium hydroxide, potassium carbonate and water, ethanol, or we can use alkoxide in alcohol to get terminal alkyne. If R aryl and R prime H or aryl, we can use sodium amide in liquid ammonia, or we can use N-butyl lithium in ether to obtain the alkyne. When 2,2-dibromo 1-phenylpropane is heated overnight with sodium amide at 150 degrees Celsius, the major product after addition of water is a full smelling compound of formula C9H8. Propose a structure for this product and give a mechanism for the account to account for its formation. Starting with 2,2-dibromo 1-phenylpropane, that is the structure, with amide first one act as a base, double bond formation, ejecting Br minus to form 2-bromo 3-phenyl prop 1-ene. Second molecule of amide again attack as a base, forming the triple bond and ejecting Br minus, forming the acetylene. Since we have said we are having sodium amide, so, and this is the terminal, sodium amide will be base to form acetylide, and that will remain in a solution until we add water to form 3-phenyl prop 1-ene. That is the structure. So when we have 2,2-dibromo-1-phenyl propane heated overnight with sodium amide, the 3-phenyl prop 1-ene will be the product. Join us in Organic Chemistry 1 and enjoy the course.